mainnet launch went incredibly smoothly. Like, I almost feel like I missed out. I wanted some drama. In order to get this sort of like vision to be successful, we needed a scale. That's when people started turning to go, okay, how do we make this more modular? If you've got 1,000 rollups, you can't have thousands of full nodes downloading the block over and over and over again.
Welcome to the Bare Metal Podcast.
Hi everyone, welcome back to the Bare Metal Podcast. This is Ship the Code from RockOX here with you, and today I've got Callum Waters from Celestia. Welcome, Callum.
Hello, nice to be on the podcast.
So can you start us off by introducing yourself and telling us a little bit about how you got into crypto?
Sure. Well, I guess I fell down that rabbit hole about 4 years ago. I just finished studying robotics and economics, and I kind of got really interested in distributed systems. And to be all honest, it was quite random that I landed a job at Tendermint. And that's where I started for the first 3 years, working as an engineer and then eventually leading the team. And then about a year ago, I switched to Celestia and started working there just all before launch and then part of launch.
Well, wild ride in crypto, I think.
Yeah, it's a TLDR.
So Celestia, of course, super interesting project of today. Can you start us off by explaining, like taking a step back and explaining this whole idea of modular thesis? I'm sure people have heard this a lot, but what's your take on modular thesis? Why do you think it's going to be a trend, and how does Celestia?
Yeah, it's definitely a trending topic, but it's something that's not a new paradigm, right? It's been around software engineering for a long time. It basically comes about because software code is so easily replicated that we had this phenomenon of modularity. And even modularity in infrastructure, which I think is where Celestia is heading, isn't something new. Like, we had the microservices architecture, which has been, something that's been around for the last couple of years. And so this is kind of just bringing these techniques that have worked, especially for scaling, and applying it to Web3. And I think that's why it's been so prominent, because scaling is something that has been an issue. It's something that we saw with Ethereum. If you look back 5 or 6 years ago, we had this idea of the world computer, and everyone was really interested in it. I think in 2020 we had the DeFi summer, where there was a lot of protocols that were building on top of Ethereum, and they kind of hit this like bottleneck where people were paying. I remember I was paying 40 or 50 euros for a transaction. And so that's when it became sort of evident that, okay, in order to get this sort of like vision to be successful, we needed a scale. And I think that's when people started turning to go, okay, how do we make this more modular? And I think specifically we were looking at, okay, the bottlenecks were in the execution layer. So how do we break up that execution layer? So we have the consensus layer could be across multiple systems, and then each of those systems have their own sort of execution layer about that. And so I think that's where the kind of origins of this sort of modularity thesis come from.
So I get how modularity is something that has happened across multiple domains. How do you think it applies specifically to crypto? Or what's your map of the modules that make up, like a blockchain?
Yeah. So as I said, we had this kind of monolithic structure where these different components were all done by one system. And you could look at like the consensus, so how we sort of produce blocks, how we sort of aggregate transactions together and serialize them, which is now kind of the role of the data availability layer. We had this sort of execution environments. So there was EVM first, and now you have a lot of like virtual machines that are coming up. I guess some of the new ones that are sort of we're seeing now is the sort of way things are heading towards this like rollup centric future, which is evident even in like Ethereum's roadmap itself. And so we'll have these RAS, or rollup as a service providers, or maybe we'll have some sort of system where you have multiple sequences. There's the idea of like shared sequences as well, where that can be sort of shared across multiple systems. So, and then I guess maybe the last one is kind of like storage. And then you've also got RPCs, like how do people sort of access that data and wallets? So like, what are the actual like gateways into the system? And so in the end, instead of just having this like one node that does all, you're kind of breaking it up into a bunch of like different nodes, some for like serving the data, some for just validating it. And then do your like light nodes are sort of like right at the edge, where that's what everyone's using to sort of verify the system itself. And I guess the whole like kind of thing we're heading towards is we want to have it so that there's a small amount of nodes that do like most of the work, and then a large amount of nodes that do a little amount of work. And that's how you sort of like scale. So you can have, millions of light nodes and maybe only a couple of hundred full nodes, which are doing the kind of like heavy lifting, and they're running all the servers, and everyone can just run off their mobile phone.
This is maybe the right place to sort of think about how Celestia fits into this. So what role does Celestia fulfill in the stack?
Yeah. So I guess conceptually we view ourselves at kind of like the bottom, like the base layer. So, and it's the sort of data availability layer here. I remember joining and I was confused for a very long time as to what Celestia did. And maybe it doesn't, it's kind of hard to explain because it is a very like niche problem. And I think the best kind of answer I came across is like Celestia can be seen as like a way of ensuring that roll-up sequences don't equivocate. So in other words, it's like a serializing mechanism. It basically takes in all these transactions, and then from all these different rollups, maybe we can just focus on one rollup. It takes all these transactions and it orders them. It dictates the order and inclusion, and it ensures that the rollup sequencer doesn't equivocate. So the rollup sequencer, if we sort of trust them, they could have sort of two sets of transactions. And so you could have a light node following one chain of transactions, and then the full nodes who are verifying following another node line of transactions. And that way, the sequencer could get away with some sort of attack. So it's really just trying to stop that one case where these like sequencers are equivocating. And by doing this, you're sort of publishing all this data on this one chain, which then agrees upon that order. And so I think there's a bit of a misconception when it comes to data availability, because it's not about persisting the data, and it's not about actually like making sure that the data is available forever. It's kind of a very ephemeral system, and because of this, we can really like hyper focus on like bandwidth and gossiping and stuff like that, and do that really well. It's more about just making sure that we have this like canonical chain, so where just all these transactions are coming in. This is the order with which you should like execute them for whatever rollup that's interested. And then like I think another way you can sort of view this is a little bit like a message broker. So the way that's kind of designed is you have like publishers and subscribers. And so the publishers are the rollup sequences, and the subscribers are all the light nodes or full nodes who are like validating. And so they subscribe to namespaces that the publishers publish on. And so the way that Celestia is divided is through these namespaces. So you publish on the namespace that you're interested in, and people who are wanting to read from that namespace and can verify just that namespace only. They don't need to verify the inclusion of the entire block. They just sample that.
So the Celestia is essentially the message bus doing the serialization between the publishers and the
Yeah, it's kind of like a decentralized Kafka.
Right. Also came to mind a very popular product for message queuing. Yeah. You already touched on this chain architecture. So, but can we deliberately sort of look at these topics? How did you guys think about the full versus light nodes design? That there are two types of nodes on Celestia, right? They're doing different amounts of work. And I'm wondering, why did you design the system this way? Is it around constraints in terms of compute or operator availability, or do you think it's best from a cost perspective? I mean, what drove the design splitting the node set into full nodes and light nodes?
Yeah, well, it kind of fascinates me that like light nodes never really took off in the way that I imagined they would. Like they were something around in the Bitcoin paper. They've been around for a while, but it still seems that a lot of systems, like if you want to bridge with Ethereum, you're still running an Ethereum full node. There's no like, Ethereum light client that you can use.
Can't have a light client. Yeah.
And I guess that kind of really kills bridging. And that's one of actually the biggest applications that maybe people didn't realize is that if you're not able to verify the state of another execution environment, then you really can't bridge with them, not really in a safe way. You're kind of having some sort of more trust assumptions with it.
Right.
And so
in particular, you'll have to trust an RPC provider that's providing access to the chain for you.
And so I think,
for example,
I guess maybe a lot of the founders also shared that same sort of idea where like we want to have a light node first kind of system where we want to be focusing on the millions of users, and they should by default all be running light nodes. They should all, and in fact, by doing so, they're actually helping to secure the system. By the fact that you have a million light nodes that are all sort of sampling, they're all making sure that their data is available, that it has been published. And at the same way, like verification should be by default. You shouldn't, have to trust any RPC endpoints. And so I think from the get-go, there was that idea in mind. And so we were specifically designing these like light nodes for that. And it was on the P2P. We weren't just using RPC, like the sort of the tenement light clients or a lot of other light clients. It was embedded in part of the system itself. So you have full nodes talking to light nodes. You can have light nodes talking to light nodes as well. They can also like talk to one another.
Very interesting take. In all honesty, I didn't realize the light node idea was targeted more toward users. I was also thinking of Celestia as having two sets of operators, right?
Yeah.
One sort of operators doing the heavy lifting, but in fact, what you're telling me now is the second class of operators that are running the light nodes are also users of the system
Yeah.
that are actually helping make it more resilient
Yeah.
in this by using it.
I guess another thing I could have added here is that like if we didn't have light nodes, that means all the rollup sequences. So the people who are like gathering all the transactions, ordering them and then submitting blobs to a namespace on Celestia, those would all have to be running Celestia full nodes as well. So the fact is that you basically kind of have these two classes. You have these validators and other like full nodes, which are just basically agreeing on the ordering and sort of propagating that to the network. So they're like amplifying it to everyone else. And then you have these like light nodes. And I guess there's two kinds of light nodes users in that sense. So there are light nodes that are like built into the rollup itself, the rollup sequencer. And so those are running on servers and running all the time. And this has been coined a little bit, and I'm not too sure about whether it's the right idea, but you have super light nodes, which is to be used by the end users in the browser, right? And those aren't to be used often.
So they're ephemeral.
Yeah, this one's, yeah. They're not supposed to be, we assume that they're not running a server, they're not constantly running, but, they still need to sample when they're trying to like verify a block. So they would submit a transaction, they want to sample that their block is available, then they like verify that their transaction was included. And then they can then do other verifications, so verify the fraud proof or the ZK proof that it's valid.
Right. I think we've repeated sampling enough times that it merits a definition. So, data availability sampling, I think, is one of the most confusing topics around data availability solutions, and it's being misinterpreted a lot. So can you explain what data availability sampling is as a process, who's sampling what, and how did Celestia solve this DAS problem? Because that requires an engineering solution, right? Mapping out how to do that.
Yeah. Okay. So if we take the naive world, imagine we didn't go for light nodes and we just had this one class full node. What would happen is that the consensus nodes or the validators would all produce a block together. They would all vote on it. They'd all agree upon it, and then every single rollup would have to like download the entire block, find the transactions in their namespace, and then execute those transactions. And then continue, and not just the sequences or the other sort of executing nodes, like full nodes of that rollup, but also the light nodes would have to do this as well. And so obviously that doesn't really scale. You can't have, if you've got 1,000 rollups, you can't have thousands of full nodes downloading the block over and over and over again. So we want to
be more specific. If I can map this out, the reason I need to download the whole block is if I want to make sure a transaction is included, right? I have to download the block header, sort of verify the checksums, and then check that my transaction is on the list.
Yeah, but not only
of those included transactions.
Not only do you need to know your transaction, you need to know every other transaction in your namespace.
Right.
Because if there was one transaction prior to your transaction that is invalid, or not just invalid, but just wasn't included, it was hidden. And so you don't actually have the full history, someone else does. And so you're executing on a different line or a different chain of state than someone else is, then you're going to miss something. And it might be there was a transaction beforehand that was invalid in some case, and you don't know it. So that's the reason why you can't just verify that your transaction made into a block. You need to know that everything in your namespace, everything by that rollup did. And so then came the idea of like, okay, rather than just downloading the whole block, can we get some sort of like probabilistic guarantee that that entire block was published, that no data was hidden, no one had when I say hidden is they basically, they have a data root that includes data that's not there, that you haven't actually found. So I guess going more deeper into the architecture, we have this concept of a square, which is a data structure that is built up of all these different shares in this like 2D array. And you're basically sampling those shares. And so by sampling, every single time you sample, you increase the chance that the entire block is available. Because the moment you get to a share and the node can't provide it, it doesn't exist, or they've tried to hide it, the validator set, you'll work out, okay, the data is not available. I'm not going to trust this block. I'm not going to continue. And then, in the future, you'll probably have it that I'm going to switch DA layer. This D layer isn't reliable. And so that's what you're going for. But like the really like innovative thing is that when the block gets bigger and bigger, you're actually having to sample more and more times to achieve that same kind of probability. So if you're wanting 99.9%, as the block gets to 2 megabytes, to 10 megabytes, 120 megabytes, 1 gigabyte, even more, you're having to sample more and more and more. And so that becomes even increasingly cumbersome on those light nodes. So in order to make sure that light nodes are actually light, this is where the erasure coding came into. And I think a lot of people have this misconception that erasure coding is just for block reconstruction. So it's just the idea that you can take those shares, and if there is a bunch of shares missing, you can reconstruct that full block again. Like, that's one aspect of it, but I think the most valuable thing is the fact that you get constant amount of samples. Because those, like, you have that one share and it's kind of spread out into all these other ones through erasure coding, it means it becomes increasingly difficult to hide data. Because if you want to hide one share, you basically have to hide a quarter of the block, because it's how it's erasure coded. And so that means...
So you need this coding, just to go back and make sure it's absolutely clear, without the erasure coding, to attain the same level of conviction, the same level of probability that no data was hidden. With growing block size, I'd have to be increasing the amount of shares I'm sampling to reach that same probability, right? But what you're saying now is you guys have applied a technique called erasure coding, which keeps the number of queries I have to make constant to hit that same conviction or probability that the data hasn't been hidden for blocks of arbitrary size. Am I getting that right?
Yeah.
For arbitrary size
They
blocks.
could be 1 gigabyte, they could be 1
So
terabyte.
this really allows scaling of the block size and throughput without increasing the load on the light nodes.
Yeah, exactly. And so it's a bit more...
That is pretty impressive that works out.
Yeah, it's actually, I really think it's like kind of the magic behind the protocol. It just put increasing load on those full nodes. Those full nodes, you take a normal block that is maybe 1 megabyte, and if you're erasure coding it 2 by 2, it means it's now roughly 4 megabytes. And there's a lot more like computation and stuff done. So we're basically taking the regular block and we're transforming that data structure into something that's sampleable. And so that requires a little bit more load on those full nodes. But it means that light nodes can remain extremely light regardless of how big the blocks are. And so that becomes great when we're aggregating 1,000 rollups together and the blocks are massive. And you're like, well, I just want to make sure that I'm only sampling 16 times.
So do the full nodes, the trade-off here, if I can sort of summarize this, is you're trading off increasing load on the full nodes that are set up to be powerful and high efficiency in order to preserve a constant level of load on all the light nodes that are going to be running pretty much everywhere.
Yeah.
Right. Is the increasing workload linear in the block size or in the amount of data I want to store, or is there a super linear difficulty? Complexity?
There's different parts of this, right? So there's the complexity in terms of computation, like actually computing, because you sort of take a block full of transactions, you build a square from it, and then you have this like namespace Merkle tree, and then you want to compute the root of that Merkle tree, and that's what you kind of like agree on. And that namespace Merkle tree can then be used to verify the inclusion or exclusion of certain transactions or certain blobs in the namespace. So there's that computation aspect.
So I was thinking about the square construction. Let's limit it to this, because I think the recursive tree construction is I think more understood. But what about the constructing the square?
Yeah, it is linear in growth. It's not non-linear. Of course, you are like for every transaction you are erasure coding it 2 by 2, but it's not that it becomes even more. I guess the problems that I would be wary of with expanding sizes of blocks is gossiping, because you want to make sure that you don't have a very like inefficient gossiping mechanism. And I think a lot of like when we sort of discuss like what are the bottlenecks of Celestia, a lot of it comes down to like bandwidth. Like computation is relatively small in terms of time when you're talking about, okay, I've agreed upon this like 1 gigabyte block, and I want to make sure that all the other validators get that 1 gigabyte block, that they agree upon it, and that we can then propagate it to the network, right? So I think a lot of it comes to bandwidth and making sure that we can get that, like the amount of message passing, the complexity of that gossiping protocol as efficient as possible.
Well, this was one of the things that always, I have to say, surprised me in Tendermint, where the gossip protocols just gossip to all the peers until peers tell me they've received a block part, and then I stop gossiping, right? So this is sort of this end-to-end. And one of our systems that we use is actually built on the fact that votes are repeated. So we gather votes from many different locations, so we can see how many times those votes are propagating around the network, which is a lot.
Yeah.
Disclaimer.
And
or
I think,
surprise. But that is a much bigger problem for Celestia if you're gossiping huge blocks, right? So have you guys built like more efficient routing algorithms? Do you guys use some sort of routing table? Do you try to reduce the amount of data going through the network?
Yeah. So this is something that we're sort of currently researching. I guess one of the things that we have already like looked to modify and change is, instead of having everything sort of naively gossip to everyone, we have something called a content addressable transaction pool. So, and this is something that's been around for a while in research, which is instead of just gossiping to everyone, I send out the hashes of the transactions that I've seen, and then people request the hashes of the transactions that they're missing.
So it's sort of like a DHT, distributed hash table style storage.
Yes, somewhat like that. Yeah. Yeah. I think a lot of early BitTorrent stuff as well, that they were all sort of using this. And yeah, I think there is a lot, and this is kind of just a first step implementation. I think there's a lot more places that we can take the sort of gossiping protocol to try improve it.
Absolutely. We've alluded to bandwidth being the main limitation, which is one of the things I guess engineering has to trade off to build Celestia, right? And all these parameters sort of aggregate into one key thing that's visible to users of Celestia, which is the block time. Block time for Celestia is 12 seconds, double the standard Tendermint time, or typical Tendermint time, which is around 5 to 6 seconds.
Yeah.
Some chains are faster, yes, but typical Tendermint chains will be around 6. So I'm curious. I mean, it does impact users, right? That means the data is published with some delay. So you guys must have spent, agonizing hours or how to tune this chain to optimally, provide the service. So why is it 12 seconds?
Yeah, that's a great question. And I guess something that maybe people from the outside don't sort of understand, but it is something as engineers we've discussed a lot because there's a big sort of trade-off in this. So, okay, so in one side of it, you want to get the time as low as possible because you want finalization as quickly as possible. So now the limiting factor on finalization, so how long it takes for a transaction to be submitted and then committed, is dependent on the DA layer, not the rollups. The sequencer itself can execute transactions lightning fast, right?
Very fast.
But,
right.
And so you could, if the DA layer was down to a fraction of a second, you could see finalization happen within a second, right? So you submit your transaction within a second, you already know that it's been committed, what the order is, and what the result of the execution is, and you can verify it. But on the other hand, the reason why we don't want it to be so short is if it was too small, then the block sizes aren't big enough. Remember, the economies of scale happen when we get bigger blocks. So the bigger the blocks can get, if we have lots of small blocks, then those light clients are still sampling a lot of times. Whereas if it's one large block that happens once every 12 seconds in our case, or it could be even longer, you could have it happen once every minute, then only once in that minute you need to sample. So I guess there was a sort of a trade-off space there. And there actually has been some preliminary discussion around kind of abstracting that away so that we've tied these two concepts together, but they don't have to be. So what I'm meaning by this is you could have blocks produced at a different rate with which you produce squares. So once I said squares are the things with which you actually have to sample, and blocks are the things that are a commitment to the ordering and inclusion of transactions. So you can basically produce blocks much quicker and then at a different rate produce a square. Right now, every single time we produce a block, we produce a square with it, and that comes together. But you could have it such that you produce blocks far quicker, and then for the light nodes itself, you produce a square every now and then. So it means the latency is still slow for light nodes, but for full nodes who are following a consensus or can verify consensus, and maybe don't care about the sampling aspect of it, they can actually execute far quicker. So then you're trying to find this middle ground between, okay, we want fast finalization times, but then we also want really large blocks that we can get the sort of efficiencies out of.
Right. And the reason you want to increase the size of the blocks is you've already designed the whole network to be sort of constant load or constant effort, regardless of block size. So it's now advantageous to aggregate into bigger blocks to keep that load on all those light clients low. So the light clients can operate on any sort of device and you can be more, say, decentralized, or more and more types of users can actually do their own verification. Okay, exactly. I didn't know that was the trade-off. So what do you guys have ideas around how many nodes you should have among the full nodes? Because that's another big trade-off that you guys have to be making, right? You've got some of this huge data. There's a lot of requirements on the operators, so there's a high economic cost. How are you thinking of what's a good number of validators to have or full nodes and validators? I'm using that maybe confusingly for other chains, but for Celestia, validators are the ones storing all the data. What's the trade-offs that you're making when you're designing the size of the set, or when you're thinking about where should these validators be, right? Yeah. Is that a factor?
Yeah. So I guess there's different aspects to this. So I guess the main one is, does increasing the amount of validators increase the amount of security? in the system. So we want to make sure that that Celestia is very secure, and potentially increasing more validators does this, but it's generally proven to be very like nonlinear. Like if you have a look at any sort of distribution of the stake within a validator set, it's, the first, 6 or 7 validators in most chains take up 1/3 of the voting power. So when it comes to adding nodes, like adding more like increasing the validator set size, there's kind of diminishing returns. And then the way that the revenue that validators generate is also very nonlinear, which makes it very difficult, because if we're looking like the economics of like what is the cost to run a node, if you're right at the end of the validator set, of course that's the person we're most concerned with, because they're probably just breaking even. The people who are right at the top of the validator set, they're doing fine. Yeah.
Hopefully they're at least breaking even. That is not the case on many chains today.
Yeah, which is a very important factor. And so and there's kind of this like natural thing, I guess, over time. Whereas if we can't make it economical for validators, they will eventually leave, which means we'll have a smaller validator set to choose from, which could mean a more centralization of power. So we want to make sure it's very okay, we have got increased costs, but where can we cut costs elsewhere? And so a good example for this is that, as I mentioned beforehand, is Celestia should be viewed as relatively ephemeral. It's not responsible for persistence of data. Once the rollup has retrieved the data in its serialized order, they're responsible generally for storing it. They can provide, look at some sort of third-party provider for it if they want to, but generally they're responsible. And so what that means is that we can really reduce storage costs. So there will always be archive nodes who decide to save all of the block history, but for every sort of running validator node, only within the sort of unbonding period, or this pruning period, is really necessary to keep. And once we've agreed what that is, you can kind of let go of that data, and so that can keep your machines a lot smaller. And then I guess the focus of the cost is bandwidth in many ways.
That's right. Yeah, totally makes sense. Are you guys making any efforts around sort of facilitating or helping the community distribute stake more evenly to avoid this very, uneven revenue distribution in the validator set? Is that sort of on the map?
I've viewed a lot of research on this, and I've seen lots of other projects try without too much success. Like eventually what happens is some sort of civil, where either validators pretend to be multiple validators if you have caps on them, or they find some sort of other way. So I think it's very difficult to kind of avoid it. I think a lot of the stuff that has been successful is just in the front end. So I think it's up to like wallets and stuff to kind of encourage their users to think about who they're staking with. A lot of people don't, right? They go, okay, look, this is the commission. Okay, that's all I care about. And so it can be a bit difficult, because you have this like network where it really relies on the stake. That's where the security comes from, and the proof of stake. But then a lot of people who have that don't really care too much, and then just sort of nominate it to whoever. So if you can sort of encourage that it's in their interest to kind of distribute the stake as evenly as possible and make them aware of that, then I think that kind of like taking it from like a social angle is probably the most successful. Yeah.
Makes sense. Yeah, I don't think in protocol measures, I haven't seen any that were particularly successful, and it's really difficult to sort of educate the community that holding a token, but you might want to support, make sure the network has long-term stake potential.
Yeah, but it's super valuable if we can. Like there's a lot to be unlocked. Like at the moment we can get it somewhat equal, it means the validators right at the end are much more like net positive in costs than they are right now. So it's not just about the fact that there is no, the distribution also increases the amount of validators that need to collude in order to sort of attack the system. You've also got it making it more economically stable. So there's a lot to be gained from just better decentralizing stake.
So we've talked about validators, mainnet. You guys have launched mainnet pretty recently. Is there anything interesting you guys have learned post-launch? Is there something that happened that you guys didn't think about or didn't expect?
Yeah. So the mainnet launch went incredibly smoothly. like I almost feel like I missed out. I wanted some drama. In some cases, I wanted to rush to the war room and have to try fix some like critical consensus
Fix,
bug.
hot patch, distribute.
And just sort of release it without testing, or I don't know, any of the sort of Wild West kind of style. But it wasn't like this. It was extremely.
You could have had a cool story for this podcast, but you guys launched perfectly, so no dice.
On that avenue, I'm not going to be able to provide a cool story because real attribute to the engineering team and the DevOps and everything behind it, because I think it was well tested. We've done a lot of work in preparing for it, not just actually the engineering team, but also the sort of the other aspects of it, making sure that all the like integrating chains knew about it. Everything was sort of all set up. Like I think the communication and marketing around it was really solid. And so it actually launched very smoothly. And we haven't actually seen too much trouble since. I think one of the most interesting aspects is the sort of like rise of inscriptions. So we've had a few inscription events, and it's a bit lost onto me what the point of inscriptions are. There probably is something behind it, but it's something that I haven't really like delved too much into. From my side, it's just a great way to like battle test the sort of system live, I guess. So it's been a good way to.
So the way I can think about inscriptions is a flash mob of people show up and they start doing transactions to like take up block space, and they write something into the memos, which turns out to be awesome later on.
Yeah. So I think
is that roughly your.
Yeah, they submit transaction. Every single transaction allows them to mint so many tokens. I think like proof of wasted block space. And so and in many cases, these inscription events, these ways of like kind of distributing, they're like a way of kind of distributing a token where people are like paying as much as they want, how much they value that token in gas fees to get that token, right? So you have this like gas war where people are paying a lot. Because they think this token is worth something. And that might actually be like a relatively good distribution model in the future for like rollups. So like in many ways, you can see this like inscription thing as there would be this evolution where people want more and more control. So maybe I want to give that token to someone else, or I want some way of like trading it, lending it. And here we go. We've got, smart contracts and we've got rollups again. So that could lead into this. But in its early stage, I think it's just great to sort of see that as an opportunity to make sure that the entire system is battle hardened. I guess inscriptions aren't the only thing. We're constantly doing this. I guess our entire like approach to improving the system, because it is a very like performance focused product, is essentially push it until it falls over, like completely bombard, like spin up our own test net of about 100 validators, bombard it with transactions, and just see what breaks. And so making sure we've got good observability, we can sort of have good metrics around it and understand, okay, where is our bottlenecks? And then, if for example, now it's looking at block propagation, okay, then we got to start looking at solutions for that. But yeah, also having it battle tested, I'm happy to see that it sort of holds up to it.
Let's think about the rollups that are building on Celestia. Any projects that are catching mind. Is there already some sort of interaction? I always felt that one of the advantages for multiple rollups using a DA solution is that it makes it easier for them to interoperate, right? They can inspect one another's blocks, which is sort of like, I guess, one of the key reasons why DAs could have network effects. I'm wondering if any of that's happening. Do you have rollups developing on top of Celestia that are somehow collaborating or already expecting to work together? What's the status?
I think the short of this is it's still very early on. There's so many discussions, so many conversations happening right now, so much sort of planning about how these things should all work together, but nothing that we can sort of say is like, okay, it's in production and it's tried and proven. I think what you mentioned is very good, and I think the IBC team, for example, have been talking a lot with Rollkit and with Celestia about how we can enable that, because there is improvements both in the fact that, okay, as a rollup, if I'm trying to interoperate with another rollup on the same DA layer, I don't actually have to we're still reading the same blocks, so I can actually see all their transactions. And if I've got a light client embedded in my rollup, I can actually verify all their transactions. So it makes interoperability also like far cheaper. And because the current like IBC model, right, is that you have these relays that take a header from one chain and then post it to another. So every single chain has everyone else's headers. So you have this like n squared effect, right? Whereas if everyone's using the same rollup, you don't have that, because everyone just publishes their own header. And rather than just getting it pushed across, I can just pull that header from the same block, because it's all within that giant global environment that you can think of. So I think it's very interesting. A lot of the stuff around interoperability is, I guess, blocked on having a good proof system. So a lot of like these bridges currently are based on consensus. So a committee agrees that this block is valid, and so we trust that committee. Whereas we're trying to head towards this proof-based world, so either fraud proof or validity proof. And so trying to get IBC or other sort of like protocols that are like interoperability based or bridge based to use proofs, so that will enable roll-up interoperability better.
Do you feel fraud proofs are a way forward? I always thought fraud proofs are a way for optimistic, engines to just like cop out and say, "Oh, somebody's computing fraud proofs." Like if something happens, a fraud proof will pop up. And I'm wondering if any fraud proofs are actually happening. Like if there are people who are computing and looking for fraudulent transactions that they could prove are incorrect. But look, I'm hoping Validiums and ZK proofs.
I guess the short is like I think in the short term it does feel like fraud proofs are valid, especially if they have some sort of like economic backing behind them. Like you could have some sort of system where you're incentivizing people to sort of execute the entire roll-up environment, check for any sort of state fraud, and then produce a proof for it and publish it on chain, and then you get some sort of reward from it, or some sort of like economic structure around it. I guess I'm not going to delve into economics. It can get quite difficult, but I think in the long term, if we had ZK proofs or validity proofs that you could produce sub-seconds for the entire state of a system, we wouldn't need fraud proofs. And so I think that the way we're heading, we're looking at we're building sort of specific system, hardware level at trying to do these kind of ZK proof stuff. And so I think we're going to head in that direction eventually. I don't know how long that sort of time span is, but where we will have, we'll most likely see kind of sovereign rollups that are like ZK VM based. And so you can have these like validity proofs that you just sort of share around. And so I think it's a far better, as you allude to, it's far better that the onus is on the sequencer who's producing this block, that they actually produce the proofs for that block and say, yeah, that state is valid, rather than they producing the block and they're waiting for someone to like also compute and be like, hey, wait a second, what's up?
I'm trying not to say trust you, bro, but I failed, so I'm just going to say it sounds a lot like the second system. But, ZK proofs, obviously wave of the future. This leads me to sort of like a closing question that I have for you, which is, what do you guys, as a Celestia project, see in the future? What are you building for? Like, what are you expecting to happen, in terms of number of rollups or additional infrastructure components, usage? Is there any thesis that you guys have that you're building forward to?
Yeah, I definitely think there is a very clear-cut vision about where we're heading. And I think there's a lot of like agreement within other ecosystems as well. Like I think a lot of people through their own sort of different ways have reached to the same conclusion about how we're going to get about this like scaling problem. And you can see this with a lot of like L1s like Near and Solana, which are also moving towards becoming data availability layers. So it's kind of clear that there's agreement on that. And so I think, there's a lot still to be done in terms of rolling. The whole thing about modularity is that it's kind of like this Unix philosophy where you do one thing, you do it right. You just focus in one thing only, right? And that's what Celestia is doing. We've kind of pieced out this thing that we want to make sure that we're the best at doing, and that we can provide a superior product to other people. But that doesn't mean we're sort of dependent on a whole bunch of other products to also evolve an entire ecosystem and to have some optionality around them. Like, okay, like we don't expect to be the only DA layer as well. And we hope that there is some competition amongst DA layers so that it allows for the rollup to be able to switch between them. And in that case, then it just becomes a race to the bottom in many ways, like who can provide the highest security for the lowest cost and the highest throughput. And which is, when it comes to engineers, it's a great problem to solve. Like engineers love solving that problem time and time again. So it's something that like we're definitely sort of configured towards. But yes, I think they'll, in the future, there still needs to be a lot of work in developing these roll-up frameworks and developing these other like subsystems, like who's going to manage storage. And what sort of like virtual machine are you going to run? But I think just looking at Celestia, we're going to remain focusing on that one thing that we're sort of set out to do, which is data availability. We're going to make sure that we can provide at the sort of lowest cost, high security and greatest throughput. And there are so many avenues as an engineer when you look at it that you can go and do that in. And I assume that, like, in many ways, competitors will kind of do the same thing. And so it's going to be a very interesting thing where it's not just this, where you're a maximalist of one sort of chain. You're going to have all these different systems that you can choose from. Like, do you want to use an OP stack or Arbitrum? What kind of DA layer do you want to choose? And so there's going to be this like real like expansion of all these different sort of solution spaces that you can go with. And I think that that's generally very healthy. It probably will end up that there's some sort of convergence in the end, and there's some agreed upon way with which we should approach the sort of system architecture. But right now we're in this like very expansion phase where, okay, there's like the sort of brainstorming that we do in our spare time of the million different possibilities we could configure something is almost paralyzing. And so to just, there's going to be a lot of this stuff, and there's going to be a lot of different ways that people are going to do it, and people are going to try and test these different ways. And I think there will be things that are more successful. I do also agree that, once we can find more like computationally efficient ways to producing ZK proofs, they will kind of rule. But it's a very like sort of exciting part at the moment, like just to kind of see this dawn of a different way of doing it. And this, I'm sort of head down focusing on the engineering of Celestia, but every now and then I get to like look up and see what everyone else is building. And it's kind of very inspiring.
Well, that sounds like an exciting future you guys are building forward to. So that's a great place, I guess, to finish the pod. So thanks very much for coming on. This was super illuminating and interesting.
Thanks. It was great discussing this stuff with you.